Hello and assalamu alaikum to the second video of AI tutorial series. Today I'll be covering this topic, which is breadth first search, such as BFS. It's a uninformed search and it is a searching algorithm that we use in AI. So the things that we need to remember is this BFS algorithm is useful in terms of AI, and the things that we need to remember in terms of demonstrating this algorithm, we will came to know about this topics, which is branching factor, state space tree, start space, goal state, and depth. So just recall these things. This is branching factor, state space tree, and start states, goal state, and depth. So we will come across to two more things, which is completeness and optimality. I'll describe them later on as we go, but just see and recall them on your mind. So BFS, breadth first search, is a searching algorithm, and where we have a tree. This is a searching algorithm tree, and you can see this is the first node. This is the first node, and this node is called start node or start state. So here you can see this is the parent of A, B, and C, and A has 3 children, D, E, F. B has 2 children, J and H. C has 2 children. So here we have I and K, and these are the 2 children of C. I think you can see them now clearly. So this is our tree, and we know one more thing from our algorithm course, that BFS is always using a queue data structure, and it is based on FIFO, first in first out. So this is the fringe or the data structure that BFS is using. So we'll try to expand these nodes so that because we want to see how we are reaching out the goal. So our target is to reach out the goal. So now we will expand this this graph, and what we are going to push here in this fringe, we are going to push this S, and S has 3 children. Who are them? A, B, and C. I'm putting out A, B, C. A, B, and C are the 3 children of S. And in terms of breadth first search, what we know is it will search from here. It will search this node, then this tree node, then this level node, and then the last node, last level. So here this is the level 1, L0, level 0, and then the level 1. This one is level 1, L1. Then we have L2, and the next one is L3. So BFS is what it is doing. It is going forward to the breadth. So what it is doing, it is visiting the root node first, and then it is going towards the depth. So now what we are going to do is we are going to expand a node from here. We are going to expand A node. This was the first in first element in the queue. So we are using FIFO. So A. So we are going to push childrens who belong to A. So we know the childrens who belong to A is D, E, and F. Then we'll push B, and who are the children of B? B has 2 children, J and H. C, D, E, F would be there. and we have two children, J and H. We are pushing them into the fringe. Then what we are going to do is we are going to push another, such as we're pushing C. We'll go sequentially because it's first in first out, so C, and C has children's. Who are the children's? I and K. Yeah, so D, E, F would be here, and H, J, H, I, K. The new two are I and K. Now we will expand D node. So D node has children's. D node has children's. No, D node is not having any children. D node doesn't have any children, but we have E, F, J, H, I, K here in the fringe. E doesn't have any children, F doesn't, so we will expand E and F, and this would be as it is. F, this would be as it is. F, here we have E is expanded, F is J, H, I'm sorry for my handwriting, and K. So now we will expand J, and we know that J have a children which is G, H, I, K, and there would be G. So here you can see that here is G. So now we will expand. So similarly we will expand H, I, K, and we will reach out the goal node which is G. So what we get this from this search algorithm, that BFS is actually reaching out the G, okay, the G or the goal or the target of this algorithm. So what we're doing, we are traversing the nodes. We are traversing from here to the leaf node, from the root to the leaf. What else BFS is doing is BFS is storing its path over an array. So we discussed about completeness and optimality. So now we will see that what is completeness. Completeness is nothing but reaching out a goal. If you have targeted that you are going to reach out a goal, and you're reaching out a goal in a searching algorithm, then your searching algorithm will be complete. In general, BFS will always reach out the goal, so that we can say that BFS is a complete search algorithm. And now let's come to the issue of optimality. Optimality is, suppose we have another goal here, like there is no F, suppose there is another goal such as G, it's G1 and this is G2, okay, G1 and G2. So now we will describe that what is optimality. Whenever we will introduce the BFS search algorithm, we will see that BFS will return this goal. This is the suboptimal, this is the optimal goal, because and this is the suboptimal goal. Because why this is optimal goal? Because you can see that we can get this in an efficient manner. BFS will go to level 2 and it will return this optimal goal first, and then it will return the next goal which is into the leaf. So that's why BFS would be optimal, because it will efficiently return the best possible goal on our state space tree. So now we will discuss two more topic, and these are time complexity, space complexity. So time and space complexity is really important. In terms of time complexity, we know the linear time complexity was big O of v plus e, but now in terms of AI, we know that we don't use linearity, we use the exponential big O of b exponential d. So what is b and what is d? B is the branching factor. We have discussed about branching factor. This is the branching factor. So this is the b from time complexity, and d is the maximum depth. D here, d is max depth. DEPT. So what is the space complexity? Space complexity is same as the time complexity, and it can be this also, b of d plus 1. So time and space complexity are same. So what is the problem? Like, what is the problem here in BFS? Is there any problem? Do you see any problem? It is complete, it is optimal, it has a time complexity, it has a space complexity. Then what is the problem that we are not always using BFS, and in terms of research and in terms of higher AI research? Why we don't use that? We don't use that because BFS is having an exponential space complexity, whereas DFS is having a linear space complexity. I will discuss this linear space complexity of DFS in my later video, where we will go through the DFS search algorithm and its simulation, and we will discuss about DFS and what limitation we face in DFS. So for now, our tutorial is ending over here on BFS search algorithm. Thank you for watching. Please remember some of the key aspects and some of the key words. One is completeness, optimality, time complexity, space complexity, branching factor, state space tree, starter space, goal state, etc. And also remember that how we are applying BFS, it's an uninformed search. And one more thing that I forgot to mention is we will apply BFS in unweighted graph, not weighted graph, unweighted graph. So unweighted graph is, what does it means? All of the weights are basically same. So this is a unweighted graph. Thank you for watching. Again, do like my video. If you like, then it would be an inspiration for me, and do subscribe to my channel. Thank you.